Yeah, let's move on to the next one. So this is the last paper of the section, and not a paper from Alibaba. This is a paper from ByteTracker. The speaker is Zhuo Jiang. He has obtained a PhD degree from Tsinghua University in 2018, and after that have been working as a postdoc in Purdue for 1 year, and now is currently working on AI networking optimization and diagnostics at ByteTracker. He and his team have many works, including hostping and RPing mesh, that have been widely deployed in production in ByteTracker and have been also been published in SDI and SIGCOMM'. Let's welcome Zhuo Jiang.
Thanks, Lee. And hello, everyone. I'm Zhuo Jiang from ByteTracker. Today, I will introduce ByteTracker, an agentless and real-time parcel-aware network probing system. This is a work jointly with Shi Xianguo, Kefei Liu, Yulin Lai, Yongbin Dong, and many other colleagues from ByteTracker. Our story begins with the 2015 SIGCOMM' paper, PMesh, and our experience of previous network monitoring and diagnosis systems are heavily built based on PMesh. And we deployed a probing agent on all data center servers and conduct probing between agents to measure RTT and packet drop rate. Furthermore, our operators check the path of anomalous probes to locate faulty devices. During the deployment, the benefits of PMesh is that it can effectively detect various network anomalies due to its actual hierarchical probing. And when network anomaly occurs, PMesh can usually detect abnormal metrics such as increased latency and packet drop rate. And we can build up network SLAs metrics from the data we collected with PMesh. However, we do find some of the shortcomings when we use PMesh during the long-term deployment. We identified several demands that the PMesh cannot effectively satisfy. The first demand is shown in these slides, is that to quickly deploy, update, and suspend agents in PMesh, both agents are deployment and updates need to take all servers into consideration. In addition, when bugs occurs, it is crucial to quickly suspend all the agents. However, these requirements are hard to achieve, especially in a large-scale data center with millions of servers. The second demand that PMesh falls short is to detect subtle packet drop on switches. We found that some higher-tier switches can experience subtle packet drops due to a failed switching chips. These packet drops trigger the retransmission of service flows, resulting in increased latency and reduced throughput. As these switches are at high network tier, many services will be affected. However, PMesh has constant end-host probe noise, and such a low packet drop rate can easily be drawn out by probe noise. The third demand is to classify network and end-host timeout probes. One insight is that network timeout probes are typically caused by network failures and should be quickly detected and located. In contrast, host timeout probes have a lot of probe noise, such as timeout caused by host reboots or CPU overload. However, PMesh cannot effectively identify network timeout probes and further use them for accurate fault detection and location. The fourth demand is to quickly and accurately track probe paths. PMesh-centric systems typically need to use traceroute or INT to additionally check the paths of anomalous probe for fault location. However, this way is time-consuming and can take several minutes. In addition, the replayed probes may take different paths if the fault result in route changes, leading to a wrong fault location. The last demand is to detect and locate silent bit flapping. To uncover corrupt packets, data center network check packet content, both by hop and end-to-end. And most corrupt packets can be detected. However, we have encountered some extreme cases where a corrupt payload can pass all packet checks and reach the target process, causing the service to crash. Unfortunately, PMesh cannot detect bit flapping, let alone locate faulty devices. So in summary, to satisfy the demand above, An ideal data center network probing and diagnosis system should have these capabilities. In particular, it should not rely on end-host agents for probing, and it can actually track probe passes in real time without the need to replay probe packets. To achieve these targets, we cannot just improve PMesh, but we must design and deploy a new network probing and diagnosis system, that is ByteTracker, what we are discuss later in this slides. So this slide shows the core workflow of ByteTracker. In ByteTracker, a server is connected to each DCI switch as a probe to generate probe tasks and launch all probes. In addition, all data center switch uses ER-span to mirror all past probes and response packets to a remote analysis server for probe path checking, fault detection, and location. For the probe data path, the probe uses a TCP SYN packet with an invalid destination port to the probe packet. After the target server receives the probe, its kernel responds with a TCP RST packet to reject the invalid connection request. This response is supported by the OS kernel, so there's no need to run a response process on the end host. Besides, as the kernel tasks have a higher process priority, this probing method has low end host probing noise. There are two types of probing in ByteTracker. They are north-south probing and east-west probing. Next, we will introduce these two probing flows and demonstrate why we need to conduct probing in two directions. In north-south probing, the prober uses a invalid SYN package to probe all the servers in the data center, as well as the other probers. With random 5-tuple north-south probing can effectively cover all switch ports, links, inter-DC connections. North-south probing is easy to deploy and can cover most data center network problems. Note that in single chip switches, all the ports connected to one switch chip. Therefore, for these switches, it is sufficient to guarantee that the probes can cover all the switch ports. However, in multi-chip switches, forwarding between some ports occurs on one switching chip, while forwarding between others is inter-chip and must traverse the switch fabric. As a result, both intra-chip and inter-chip forwarding can fail. Therefore, for multi-chip switches, probe packets must cover not only all ports, but also all forwarding logic. To further cover all forwarding logic in multi-chip switches, we add east-west probing in ByteTracker. To achieve this target, east-west probing requires probes to be sent from a tier below the multi-chip switches and forwarded by them within the same tier. However, as the probe is located in the highest tier of the data center network, it cannot directly achieve this goal. To solve this problem, the prober sends IP-in-IP encapsulated SYN probe to a TOR switch. The switch will then decapsulate and redirect this probe to the target server. In this way, east-west probes can effectively cover multi-chip switches for forwarding logic. For the timeout classification, the probe sends multiple probes in parallel and classifies timeout based on timeout numbers. These probes use different source ports to be hashed to different passes. Typically, concurrent probes on parallel passes can reach the target server at almost the same time. Therefore, host anomalies will usually cause most probes in a group to time out. In contrast, if only a small number of probes in a group experience timeout, the prober infers that the cause is in the network. The design philosophy is that it is very rare for multiple parallel paths to drop packets at the same time. Next, we will introduce the process to accurately locate the network packet drop. This slide shows the normal forwarding and mirroring process of probe packets. The ER-span features on the switch mirrors probe packets before forwarding them. For most cases, switch can mirror probe packet before dropping them. In this scenario, packet drop location is straightforward. The analyzer can easily identify anomalous switches by checking where the network timeout probes were last captured. This simple fault location logic is due to the collection of pure network timeout probes and accurate probe passes. In some extreme cases, the faulty switching chip may not only cause packet drop in forwarding, but also prevent those packets from being mirrored normally. In this scenario, the timeout probes are last mirrored in last hop switches, and a lot of last hop switches will be marked as failed. When this happens, the analyzer will further inspect the number of mirrored packets on switches. The number usually decreases significantly on the faulty switches. With packet mirroring, the analyzer can compile the mirrored probe hop by hop to detect silent bit flipping and directly locate where these probes were modified. Since the switch mirrors probes before forwarding them, if the analyzer finds that the packet mirrored by a switch is corrupted, it usually means that the packet was modified while being forwarded from the last hop switches to this one. We have deployed ByteTracker in all of our data centers, and we evaluate ByteTracker's performance in a data center with hundreds of thousands of servers. During the half-year evaluation, ByteTracker effectively detected 276 network anomalies, including subtle packet drops, silent bit flipping,